Hey everyone, welcome back. This is lesson 11 for compound events. By the end of this lesson, you're going to be able to find the probability of mutually exclusive events. You'll also be able to find the probability of inclusive events. Your vocabulary for today is simple event, compound event, mutually exclusive events, and inclusive events. A simple event is an event that describes a single outcome. For instance, rolling a cube die, you roll the die and you're going to have one outcome, one number comes up at the top. A compound event is an event made up of two or more simple events, and mutually exclusive events are events that cannot both occur in the same trial of an experiment. For example, rolling a 1 and rolling a 2 on the same roll of a number cube are mutually exclusive events. It cannot happen. So you'll have event A and event B, and they'll never be happen at the same time. So those are called mutually exclusive events. So here's a chart for us. It's going to be real helpful, telling us about mutually exclusive events. So in words, the probability of two mutually exclusive events, A or B, occurring is the sum of their individual probabilities. So algebraically, for two mutually exclusive events, A and B, the probability of A or B, so remember that little U sign means union or. And so that the probability of one or the other is probability of A plus probability of B. All right, here's an example. A group of students is donating blood during a blood drive. A student has a 2 out of 5 probability of having type O blood and a 9 out of 20 probability of having type A blood. The question says, explain why the events type O and type A blood are mutually exclusive. Well, it's pretty obvious. A person can only have one blood type. You can't have type A and type O at the same time. So those are mutually exclusive events. Here's another example. A group of students is donating blood during a blood drive. A student has a 2 out of 5 probability of having type O blood and a probability of having type A blood of 9 out of 20. What is the probability that a student has type O or type A blood? So there's that word or. Remember, that would be a union. And when we see that, that tells us we're going to add. So we're going to add the two type probabilities together. 9 over 20 plus 2 over 5. We have to get a common denominator. Don't forget that. And we end up with 17 out of 20 is our probability. All right, so try this one on your own. Turn your video off and give it a try. All right, so this problem says each student casts one vote for senior class president. Of the students, 25% voted for Hunt, 20% voted for Klein, and 55% for Villa. A student from the senior class is selected at random. Explain why the events voted for Hunt, voted for Klein, and voted for Villa are mutually exclusive. And you should have said, because each student can only vote once. They can't vote for twice. They can't have two events, just one outcome. All right, here's another part of the question to try on your own. Again, turn the video off and try it on your own. All right, so again, we have the same information. It says a student from the senior class is selected at random. What is the probability that a student voted for Klein or Villa? So there's our word or, so that tells us a union, and that tells us that we want to add our two probabilities together. So the probability of voting for Klein was 20%, so that's 20 out of 100, and the probability of voting for Villa is 55%. So when we add those two together, 25% or 20% plus 55%, we get 75%. Okay, so inclusive events are events that have one or more outcomes in common. When you roll a number cube, the outcomes rolling an even number and rolling a prime number are not mutually exclusive. The number 2 is both prime and even, so the events are inclusive. All right, so I hope you noticed that word and. That's going to be a helpful word to us. So you can take a look at these two sets, even numbers and prime numbers, and 2 is both even and prime. It's the only one, but it is one that is even and prime. So notice now I have this upside down U, and we've talked about that before, that upside down kind of looks like an A to me, and that would stand for and. All right. Next. All right, so there are 3 ways to roll an even number, 2, 4, and 6. And there are 3 ways to roll a prime number, 2, 3, and 5. The outcome 2 is counted twice when outcomes are added, 3 plus 3. The actual number of ways to roll an even number or a prime number is 3 plus 3 minus 1 equals 5. The concept of subtracting the outcomes that are counted twice leads to the following probability formula. All right, so here's a chart that's going to tell us about inclusive events. So in words, the probability of 2 inclusive events, A or B, occurring is the sum of their individual probabilities minus the probability of both occurring. So for example, in algebraic terms, for 2 inclusive events, A and B, the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. All right, and so here's an example. When you roll a number Q, the probability of an even number or prime number is equal to the probability of the even or prime, which is equal to the probability of the even plus the probability of the prime minus the probability of the even and the prime. So again, just remember that when you see this symbol, it means and I always try and make it so that I can see that A in it. All right. All right, so I hope this example will help you understand this a little bit better. It says find the probability of a number cube rolling a 4 or an even number. So the first thing we want to do is take a look at what is the probability of rolling a 4. Probability of rolling a 4, there's only 1 4 out of 6, so it's going to be 1 out of 6. Now the probability of rolling an even number, there is 2, 4, and 6. 2, 4, and 6. And so that tells us there are 3 even ones. Now, what is the probability of rolling a 4? Probability of running a 4 and an even. Well, if we look at all the numbers, the only one that is 4 and even is the number 4. 4 is both the number 4 and even. It's the only one. So the probability of both of those is 1 over 6. Okay, so now that we have that information, now we can take a look at our formula. So we're going to take the probability of rolling a 4, 1 6, plus the probability of rolling an even, 3 6, and now we're going to subtract out of there that one that is in both of them. We're going to subtract that out, and so that's going to be our 1 6. So remembering that 4 is also an even number, I see the probability of rolling a 4 here, the probability of rolling an even here, and then we're going to take this last 4 out because it's in both of those categories and we don't need to count it twice. So once we add it up, we end up with 3 6, which is the same as 1. Okay, so here's another one to try. It says rolling an odd number or a number greater than 2. So our formula, we need to find the probability of getting an odd. Well, our odd numbers are going to be 1, 2, 3, 4, 5, and 6. So I see that I have 1, 2, 3. So 3 out of 6 are odd. All right, now the probability of getting something greater than 2, so that's going to be 3, 4, 5, and 6, so 4 out of 6. Now, I need to know which ones are odd and greater than 2, so I can see that it's going to be the 3 and the 5 are both odd and both greater than 2. So that tells me that the probability of getting a 3 or a 5 is 2 out of 6. All right, so now I can just add and then subtract. So I'm going to add 3, 6 plus 4, 6 minus 2, 6, and I end up with 5, 6. So there's my probability. All right, so turn your video off and see if you can do this one on your own. All right, this time we're dealing with a deck of cards, and we want to know the probability of drawing a king or a heart. So first of all, we want to find the probability of drawing a king. Well, I know that there are 4 kings in a deck of cards, so there's 4 out of 52. Now, in our deck of cards, I have, how many hearts do I have? I actually have 13 out of 52. And of those, how many of them are a king and a heart? Well, I know there's only 1 out of 52. All right. So when I add my 4 out of 52 plus my 13 out of 52, I get 17 over 52 minus 1 over 52 is 16 over 52. And 4 goes into that 16 4 times. 4 goes into 52 13 times. So we can see that the answer is 4 out of 13. All right, try this one on your own. Turn the video off. Give it a try. Okay, this one's just a little bit more complicated, but not too bad. We're trying to draw a red card, which means hearts or diamonds, or a face card, jack, queen, or king. So the first thing we want to do is go ahead and get our formula written out. And the first thing we want to find out is what is the probability of getting a red card? Well, I've got hearts and diamonds, so that's going to be 26 out of 52. Now, how many face cards do I have? Well, I have 4, 8, 12, 4 of each, jack and hearts, diamonds, clubs, and spades. So I have 12 out of 52. All right, so next I need to find out how many are both red and a face card. Okay, well, I know that the red ones, I'm going to have a jack of diamonds and a jack of hearts, a queen of diamonds, queen of hearts, and a king of diamonds and a king of hearts. So that's 2, 4, 6. So 6 out of 52. All right, so now when we go ahead and add all that together and then subtract, we end up with 8 out of 13, and that's our probability. All right, let's take a look at example number 3 now. Of the 1,560 students surveyed, 840 were seniors and 630 read a daily paper. The rest of the students were juniors. Only 215 of the paper readers were juniors. What is the probability that a student was a senior or read a daily paper? All right, so let's take this information and see if we can figure out a few things about it. First of all, we could use a Venn diagram and try and label all this. Now, our paper says that only 215 of the paper readers were juniors. So if we have this yellow circle as readers, and these 215 are our juniors, and we know that we have 630 readers in all. So 630 readers in all, and 215 of them are juniors. That tells me that 415 of the readers are actually seniors, okay? They are readers and they are seniors. All right, so now I know that there are 840 seniors in all, and I know that 415 of them are actually the readers. So we're going to subtract that, and we end up with 425 seniors. All right, so we have 425 seniors that are not readers, 415 seniors that are readers, and 215 juniors that are readers. So the part that we're really going to be really super interested in is this 415. So let's go on and see what to do next. Okay, so step 2 we've actually already done. We figured out the number of senior paper readers, and we figured out that that was 415. Okay, so now we can find the probability, and the first thing we're going to do is take a look at the seniors. And so our seniors, we know that there were 840 seniors out of 1,560. For our paper readers, we know that we had 630 out of 160. And finally, our seniors that read papers, or that read papers, is 415 out of 1,560. So putting that all in, we come to the conclusion that the probability that the student was a senior or read the daily paper is about 67.6%. And here is the Venn diagram, again, totally filled in, just like we did at the very beginning of the problem. So there it is. All right, it's time for you to get to try one on your own. Turn the video off and give it a try. Okay, so let's get going. It says, of 160 beauty spa customers, 96 had a hairstyling and 61 had a manicure. There were 28 customers who had only a manicure. What is the probability that a customer had a hairstyling or a manicure? All right, so let's think about all the information that So the first thing we want to do, again, is use a Venn diagram. And let's go ahead and talk about what we know. Let's fill in as much information as we can. So the first thing that we look for is that it says that there were 28 customers who had only a manicure. So we're going to put that in this section right here, 28 that had only a manicure. Now I know that there were 61 manicures in all. So 61 minus 28 is actually 33. So I know in this other pile I have to have 33. So now if I know that I had 96 hairstylings and manicures and 33 of them were manicures, 96 minus 33 equals 63. So that's where I get my 63. 63 people just had hairstyling. 28 just had manicures, but 33 had hairstyling and manicures. So notice they're in the middle here of our Venn diagram. So now we already have all of the information that we're going to need. We're going to use this plus this, and then we're going to subtract those that are in the middle, the 33 in the middle. All right, so let's take a look at our information here. We have to find the probabilities, and the probabilities of people getting their hair done, there were 96 out of the 160. There were 61 that got manicures, and then this 33 that had hair and manicures is 33. So we're going to subtract that, and we end up with 31 over 40. So that tells us that the probability that a customer had a hairstyling or a manicure is 77.5%. All right, so recall from lesson 11-12 that the complement of an event with probability P, all outcomes that are not in the event, has a probability of 1 minus the probability of the event happening. You can use the complement to find the probability of a compound event. Let me just talk about what that means for a minute longer before we move on. So if I know that there is a 30% chance of rain, I know that there's also a 70% chance of not rain. So if the question says, what is the chance of not rain? Well, I can find out the percentage of rain and just say 100% minus that 30% equals 70%. So in order to find the not an event, like what's the percent chance of it not raining, I just take the percent of it raining and subtract from 100. All right, so this example says each of 6 students randomly chooses a butterfly from a list of 8 types. What is the probability that at least 2 students choose the same butterfly? So let's see what we do for that. The first thing we want to do is think about using the complement, okay, just like we talked about a minute ago. So at least 2 students choose the same. We're looking for that probability. So it's going to be 1 minus the probability that all choose different. All right. All right, so now we're going to put everything we know together to answer this problem. So first of all, we need to know the total number of possible ways that 6 students can choose different butterflies. So this is actually a permutation because order does matter. And so we're going to use the permutation rule, and we have a total of 8 different butterflies, and we're going to have 6 people choosing. So we're going to remember that permutations like this is going to be n factorial divided by n minus r factorial. So our n is 8. So it's going to be 8 times 7 times 6 times 5 times 1. And n minus r, 8 minus 6 is 2. So we're going to say 2 times 1. So these cross out. So we are left with 30 times 4 is 120 times 56. All right, so this is a pretty large number, and we'll work that out in just a minute here. And then the number of ways that 6 students can choose butterflies. Well, each student is going to choose, and they'll have 8 choices. So student 1 has 8 choices. Student 2 has 8 choices. All right, and 3, 8, 8, 8. So we're going to end up with 8 to the 6th power when we multiply all those together. So here we have our permutations divided by our total number of choices, which equals, and here it is, this huge number, divided by this equals this amount, okay, 0.0769. So that's our probability that you choose all different. But that's not quite what our question said. Our question said at least 2 choose the same. So we're going to say 1 minus 0.0769 equals 0.9231. So in the end, our probability that at least 2 students choose the same butterfly is about 0.9231 or 92.31%. Remember, you just have to move your decimal point 2 places over. All right, so now it's your turn to try one on your own. Turn your video off and see if you can do this. All right, so this one says in one day, 5 different customers bought earrings from the same jewelry store. The store offers 62 different styles. Find the probability that at least two customers bought the same style. All right, so first thing that we need to think about is that we're going to be using the complement. And so we know that 2 customers bought the same earrings. So that's going to be 1 minus the probability that all choose different. Okay, so there's something different between the same and different. So we got to find the probability that all choose different. So let's do that. Okay, so the first thing we want to do is find the probability that all choose different. All right, so in order to do that, we're going to again use permutation. Show that the number of ways 5 customers can choose different earrings. So I'm going to use my permutation. I have 62 different choices to choose from, and I'm going to choose 5. So you can put that in your calculator. And then down here, the total number of ways 5 customers can choose earrings. Again, I have 62 choices, and I'm going to have 5 different customers, and each customer has 62 choices to choose from. So we end up with 62 to the 5th power. All right, so now that I have that, I'm just going to either write it out, but I'm not going to. I'm going to put it in my calculator, and here is our answer. But this is the answer to the probability that all choose different. And my question said that, what is the probability that at least 2 choose the same? So I'm going to use the difference, okay? So at least choose the same. So I'm going to say 100% minus 0.8476, and that leaves me with 0.1524. And the conclusion is that the probability that at least 2 customers buy the same style is about 0.1524 or 15.24%. And that is the end of your video. You have made it through the end of the year. There's no more videos for you in Algebra 2. So I hope you learned a lot this year, and I will see you soon. Have a great day. Bye.